Welcome to the 6th lecture of special relativity. So today we will see some very nice consequences of the Lorentz transformations. So over the last few lectures, we derived in two different ways these Lorentz transformations, which are basically the transformations between coordinates of a space-time between two frames, a frame O and a frame O prime, which is moving at the speed v with respect to the system O, okay? Now, something that I would like to kind of stress in this lecture is the following. I am assuming, so basically people has different motivations in life. There is a lot of people, and that's kind of geeks, nerds, physicists, you know, they overlap very much. And for us, what is important is to understand the truth and to understand how the universe works, okay? Now, we are lazy, we are mostly lazy. However, if we need to work a bit hard to understand how the universe works, that wins, okay? And the important thing is that these transformations are how the universe works, okay? So the Galilean transformations, they are fine, but they are just an approximation, okay? They are an approximation if the speeds between the two systems are really small compared to the speed of light. But although you need an effort to understand special relativity, a very important thing about special relativity, it really described how space-time works, okay? Now, since 2000 years, scientists have been wondering what is the nature of space and time. And now, or like 100 years ago, for the first time, we are really understanding it, okay? So this is an historic moment. So we are all very lucky that we can study this, okay? So I know some things are not super easy, but please, like, if your aim, right, it is to really understand how the universe works, then you should need, and you do need to understand this, okay? Okay, so these, on the other hand, these transformations have crazy consequences, and today we will describe, so we have been seeing some of the consequences, and let's describe another consequence today, which is super nice. So we will see what is known as time dilation. And imagine that O prime carries a clock, okay? That ticks with period delta, okay? So delta could be 1 second, could be 1 week, could be 1 month. Every second, tick, tick, tick. The question is, what is this period according to O, okay? And this is very easy to answer with the formulas we have just derived. Because the ticks, these ticks, or the clicks, are events at Ct prime x prime equals nc delta 0 with n equals 0, 1, 2, 3, 3, ... Okay? So each of these events, they represent the clock of O prime ticking at times equals delta, 2 delta, 3 delta, 4 delta. Is that okay? Yeah? Beautiful. So for O, these events are very easy to see where they are at. Because we just use this transformation, okay? We just use the Lorentz transformation without thinking too much about it. And this is given by gamma, 1 V over C, V over C1, and C delta 0, okay? But then we just can compute the time t that these clicks corresponds to, and we see that the time between clicks for O is gamma times delta, okay? Because of this factor gamma here. Now, this factor gamma is bigger than 1, okay, for any speed. So that means that this is bigger than delta, all right? For instance, if the speed v is equal to a square root of 3 over 2 times the speed of light, then this gamma is exactly 2, okay? Just to give an example. And by increasing the speed and getting closer and closer to the speed of light, you can make this gamma bigger and bigger and bigger, okay? Beautiful. Now, when you think of clocks in special relativity, you are thinking about something that could be very sophisticated. It doesn't have to be sophisticated. Imagine that O prime is in a spaceship, okay? And delta is 1 year. And every time that this delta comes, they celebrate their birthday, okay? That's the click. The click is a biological thing. It could be they celebrate their birthday. However, if they are moving with respect to me, what I will see is that they celebrate their birthday every 2 years from my point of view. And they age 1 year every 2 years for me, okay? They really do age less if they are moving with respect to me, okay? This is real. So the clock could be a biological clock, and this is true, okay? And in 2-3 lectures, I will describe an experiment in particle physics where we see this, and we see this happening, okay? And in the example I will give, the speed is more than 90% the speed of light. So we will see things aging way, way less, okay? Okay, there will be muons, not people, but it is true, okay? And this effect leads to something quite famous, which is the twin paradox. So the twin paradox, you have to choose 2 twins. One of them has to start with A, let's say Alice, and the other one has to start with B, for instance, Bob, okay? It could be Alfredo and Beatriz or any other names, but following the general literature, we will choose Alice and Bob, okay? So what happens in the paradox is that Alice, they are born, okay? So t is equal to 0, very easily. And as soon as they are born, Alice stays on Earth, okay? And Bob goes to a faraway planet, okay? At some speed, which is almost the speed of light. It's very fast, right? So Bob goes to the planet. So as Bob goes to the planet, Alice sees that after time t in Alice frame, which is just Earth, okay? Bob reaches the planet, okay? And then, when he arrives to the planet, okay, he comes back to Earth. Fair enough. So at the same speed, okay? So he goes to the planet at the speed v, quite fast, and he comes back also at the speed v, okay? Now, according to Alice, the time that Alice sees, this is 2t, let's say, okay? So Bob has reached the planet, and then he comes back. And imagine that whenever he's traveling, okay, he celebrates his birthdays. Why not? Okay? But what Alice will see is that he celebrates a birthday every 2 years. Let's say that he moves at this speed. Okay? And when he comes back, he also celebrates his birthdays every 2 years. So that when they are back together, Bob is much younger than Alice. Okay? Because of this factor. All right? So, the time for Bob, the time that has h, that Bob has h, is 2t over this factor gamma, which is bigger than 1. Okay? Any questions so far? Yes?
So Bob experiences time the same way?
That's a very good point. So what we are seeing, right, so now it will come the paradox. So Bob experiences the time in exactly the same way, okay? So if you are moving at the speed v, no matter how fast the speed is, you will experience time in exactly the same way because that was one of our postulates. Our postulates tell us that if our speed is constant, we are just an inertial frame. So Bob is an inertial frame. It's moving at a constant speed v. No matter how close to the speed of light Bob is going, the speed is constant, it's an inertial frame. There is no experiment, nothing that Bob can do that can show that Bob is actually moving, right? Because he's moving with respect to Alice, all right? So, but the point is that then Bob comes back, and when he comes back, they see each other, okay? And Bob is younger. But now it comes the paradox, right? Because we are seeing things from the point of view of Alice, okay? Let's have a look at the things from the point of view of Bob. From the point of view of Bob, Bob is put in his spaceship. Alice takes Earth with her, moves at the speed v, all with the Earth, okay? It reaches some point and then comes back with the whole Earth, okay? Why not? And when she does that, she should be younger, okay? Yeah? So the question is, what is going on? Who is younger of the two? Yeah? And that is the paradox. That is the twin paradox. So people have done science fiction movies with it. That they have done all kind of crazy stuff. Now, beautiful. Let's solve the paradox. Let's understand the paradox, and let's see why it is not a paradox, okay? So the resolution of the paradox, is that Bob has to come back. And in order to come back, he needs to accelerate. Okay? And when he needs to accelerate, he's changing frame. all right? Because his speed first is v, and then is minus v. So the frame changes. So that the situation is not symmetric, because Bob, when at the speed v, has to turn back, actually accelerating, and in this acceleration, he was not an inertial frame anymore, okay? And actually, so that when they meet, Bob is actually younger, all right? Because the Alice is an inertial frame all the time. So this conclusion by Alice is true, but the conclusions by Bob are not true because he was not an inertial frame. Okay? Let's do some pictures that will show that that is very clear. Now, in the problem sheet, you will have to solve a beautiful problem of two twins that depart and they send beams of light to each other every year. But this is like a very version of that. So let's try to plot something very nice. So this is Alice, okay? And this is the system of Alice. Sorry, this should be a straight line, okay? And this E is the time at which they are born and Bob lives, okay, to planet P. So this one here, let's say here, is, this is time t for Alice. And this event V is where Bob reaches the planet. So this is Bob, like this. And you see that when Bob travels to the planet, he is in an inertial frame, like this, which we will call O prime, okay? However, whenever Bob now has to go back to Earth, he has to change frame, and this angle should be the same. So this is Bob going back to Earth. And this one here is another system which we denote O prime prime, okay? So actually, in this picture, there are three inertial frames. There is the inertial frame O, which is Earth. There is the inertial frame of Bob going there to the planet, which is O prime. And there is the inertial frame of Bob returning, which is the frame O prime prime, okay? And this event P is Bob reaching the planet. Any questions about this? No, it's good. Good, yes.
If you were to derive everything from Bob's perspective,
Yes.
you were to do the Lorentz transformation into O prime and then into O double prime, would you derive the exact same thing as what Alice sees?
Beautiful. Beautiful. Yes. Now let's try to do something like this. Fantastic. Fantastic. Thank you. Yes, that's fantastic. That's what we are kind of about to do, but we will just drop something. Indeed. Beautiful. Yeah, absolutely. I mean, you could do, and we will do something like that in a second. Indeed, you could have drawn this axis straight, right? And then the axis of Alice would be a little bit to the left. Indeed. But the problem is that when Bob comes back, he needs to change reference frame to O prime prime, right? And so there is this system. But let's try to see the following. So why? So this event, so let's draw three events. Let's call this y, which is what we call time t, okay? And this y, what does it mean? Is when Alice thinks Bob reached the planet, okay? Beautiful. But let's try to answer the question that you are asking. Let's imagine now that this system, let's take the system O prime, okay? And in this system O prime, let's draw the axis. Remember, it has to be, so this is the axis t prime equals constant, right? So this is the t prime of the event p, okay? So this point here, if you do this point here, which we call x, so what this x means, this x is how old Bob thinks Alice is when he reaches the planet, okay? Answering exactly your question. So from the point of view of Bob, okay, when he reaches the planet, this is the line x prime equals 0, and this is the line t prime equals a constant, okay, from the point of view of Bob. So that if he wants to see how old Alice is, he has to continue this line, t prime p, and see the intersection of that with the line of Alice, okay? So what he thinks the age of Alice is, when he reaches the planet, he thinks Alice is a bit younger, okay? And this is this factor, is t over gamma, basically, okay? So from the point of view of Bob, he thinks that Alice is younger when he reaches the planet, okay? So from the point of view of Alice, Alice thinks Bob is younger, but from the point of view of Bob, exactly the same happens, and Bob thinks Alice is younger, okay? But now, there is something very cool. So Bob is going to the planet. He starts feeling nostalgia for Earth. I don't know if that is an English word, but I think you understand. He misses Earth, which is funny because he was never on Earth. He departed as soon as he was born. But let's say he wants to be on Earth, then he starts going back, okay? Now, when he starts to go back, he changes to this system here, okay? Now, this system, O prime prime, has some t prime prime of p, which is given by this line. So there is another event here, and here is where it gets a bit crazy, but it's the resolution of the paradox. So this event set is how old Bob thinks Alice is when he starts going back, okay? Because he has to change a reference frame in order to start going back. Now, he thinks that the age of Alice went from X to Z. So from his point of view, what is happening actually, and this is true, is that as he goes back, he sees that Alice suddenly became 2 years older just because he came back. Okay, just this turnaround from his point of view, makes Alice to grow older in his view. Okay, so that when they are together, indeed, Alice is older and there is no paradox. Okay, so this turning here and Alice from the point of view of Bob jumping from X to Y is from X to Z is the resolution of the twin paradox, which is not that paradox at all. Is that okay? Yes.
So is it the case that Bob's perspective, at every point other than the turnaround, Alice is aging slower for him?
Yes.
And then the turnaround just makes it so that overall she's actually aged more.
Beautiful.
So it overcorrects for the...
100%.
Okay.
That is exactly what's going on, yes.
So would it be that in the process of accelerating and decelerating, this aging actually happens like smoothly rather than being
Absolutely. Yeah, absolutely. So here, although this is a tip, you could imagine that in real life, you have to start decelerating and then accelerating back, indeed. So this would be more round, if you wish. So this happens, in a smooth way. So that's what would happen in real life. Yeah. Yes.
So does the length of time at which you accelerate and decelerate affect?
That's a beautiful question, actually. So, okay. So if you want to understand acceleration super precisely, you would have to go into the realm of general relativity. However, for this problem, you can make this as small as you want, and the conclusions of the problems do not change. We will deal with accelerated motion, actually, towards in a few lectures from now, and you will see. So it's no gravity. I mean, there is a lot to say about acceleration and gravity, why they are the same thing, etc. But basically, one can deal with acceleration without using general relativity, and that's what we will do. But one could do a more careful analysis. But basically, this conclusion doesn't depend on these details, because you could do this smoothly, but in such a way that it's as small as possible, so to say. Okay? And it's so one paradox less in your lives. Any other question? Beautiful. Very nice. Oh, beautiful. Yeah. This is nice. So now let's solve another very nice problem. And again, let me use this here. And here to do some problems. So the problem we want to show, to solve, is, can you see if you're right here? Yeah. Is addition of velocities, okay? In special relativity. I told you that you cannot add up velocities, but what do you do, okay? And we will find the answer to that. It's a beautiful, beautiful answer. So what we are imagining now is that we have three systems, O prime, and O prime prime. And O prime, we imagine that is traveling at velocity u with respect to O, okay? And this one here is traveling at velocity v with respect to O prime, okay? And what we want to find is W, which is the velocity of O prime prime with respect to O, okay? And we want to find in usual Galilean mechanics, W would be U plus V. Here, that's not true. Okay? So that's what we want to solve. So yeah, just in the Galilean problem, you would have a system O, which let's say is static. Then you would have a system O prime, which is moving at the speed u, right? And now you need to imagine a system O prime prime, which is moving at the speed v with respect to O prime. Okay? So that in usual Galilean mechanics, W would be the sum of these two velocities. Is that okay? Is it okay?
We were just thinking, or I was thinking, if O prime is traveling at velocity v with respect to O, then surely O and O double prime are the same, or is it because?
So U is traveling with respect to O, and this guy O prime prime is traveling at velocity v with respect to O prime. Yeah. So basically, imagine an ant, right? And the ant is moving at 1 meter per second in the direction forward to my notebook, okay?
But it's velocity, not speed, but we care about the direction.
Right. It's always in the positive x. Yeah, I apologize. Yeah. So it's always, let's say, positive x. We are in one dimension, so we will work in more than one dimension later. But here it's just one dimension, and they are moving in the positive direction. Yeah. Sorry, you're right. So it's velocity, let's say u and v, and both of them are positive. Okay? Yeah? So it's clear what the problem is? Beautiful. So now, in a special relativity, always you need to plot diagrams. Okay? And plotting diagrams is super helpful. It's the way to go. And let's plot a diagram here. Yeah, let me draw it here. So first, this is the system O. Okay? And this is the system O prime, which is moving at a velocity u with respect to O, and O prime prime, which is moving at a velocity w, which is what I want to find, what we want to find. Or we could draw the same from the point of view of O prime. So this would be exactly what you were suggesting. And then O would be here, right? And O prime prime would be here, okay? Moving at a velocity v. Yeah? And now we look at one event, and we look at one event, the same event, from both points of view. So this is the event A, and the event E is where everyone coincides. So this is the event E, and the event A is somewhere here. Okay? Beautiful. So now we are going to be very careful. Okay? So we are going to write down a few equations. If you do not understand any of these equations, please stop me. Beautiful. So first we will write the coordinates of the events E and A in O prime. Okay? Well, that's very easy. So T prime of E and X prime of E have to be 0, because that's just the origin. Okay? Sorry, the origin should be like here. And T prime of A, we call it T prime, and X prime of A is some X prime, but notice that because the event A is in the word line of O prime, and we are saying that O prime is moving at a speed, at velocity v with respect to O prime, then this x prime has to be v t prime. Okay? Yeah? Yeah. So that's everything from the point of view of O prime. All right? Beautiful. Yeah. So now I want to know what are the same events in O. Okay? And for that, we used our beloved Lorentz transformations. Okay? With the speed u, which is the speed at which O prime is moving with respect to O. Okay? So we just use Lorentz. Very easy. Easy peasy. So, from this point of view, t of E is actually 0, and x of E is also 0. Very easy, so it's just the Lorentz transformations of 0, 0. While c t of A is just this transform. You need to transform this, put in the matrix on the right, and then you find gamma of u, ct prime, plus u over c x prime, while x of A is gamma of u, x prime plus u t prime. Okay? So this is just applying the Lorentz transformations. Sorry. To this event A. Beautiful. But then, once we have this, we can compute W, right? And here, remember that x prime is vt prime, and W, because A is in the word line of O prime, we should be able to compute W by taking xa divided ta. Okay? Yeah? We just take this, use this, and we find the following beautiful formula: u plus v divided 1 plus uv over c squared. This is the way you add velocities in real life, when the velocities are not small compared to the speed of light. Okay? So velocities, they don't quite add up, but there is this extra factor. Okay? And in particular, of course, if u and v are small compared to the speed of light, you just add them up. But if they are not small, then you need to take this thing into account. And this is the way you add velocities. Something beautiful about this is that if you add up two velocities that are almost at the speed of light, the sum can never be bigger than the speed of light. So whatever you add up, you can never reach the speed of light. And that formula beautifully takes care of this. Is that okay? Questions? Yes?
If you have a big negative u and a big positive v, that denominator gets very large very quickly. What's the physical phenomenon that that's kind of corresponding to?
Okay, so here in the diagrams, etc., I have assumed u and v are bigger than 0 because this is a bit simpler. It's a nice exercise to assume that some of them are negative, but then you would have to use like slightly different transformations.
Okay, so that is not valid.
Yeah, that's for u and v positive, let's say, yeah. Yeah, I mean, here you would have to be a bit careful here. So, and in the diagrams, one diagram would be to the left and another diagram would be to the right. But actually, it's not super complicated. Basically, you can see that from that point of view, you could say, yeah, you could start with this diagram, let's say. So the starting point would be this diagram, right? And then you would like to find the difference between this and this. Yeah, so you can find this from here, but you have to be slightly careful. Yeah, but this is a very good question. Yeah, but even so, you can never reach speeds bigger than the speed of light. Yeah. Yeah. I think probably this works even if U and V are negative. I would have to think a little bit, but probably there is fine, like either way. But we will deduce even more than this. We will deduce in 3 dimensions, and that will be the full-fledged addition of velocities. Is that okay? Yeah? Beautiful. So I know that all of you loves group theory, so we will, do you like group theory or you don't like group? Yeah, that's very good, yeah. So, beautiful. So what we will show, and we will develop that the next lecture, but we will describe from a very nice point of view, from a kind of group theory point of view, the Lorentz group in 1+1 dimensions. And the Lorentz group in 1+1 dimensions, as we will see very quickly, is something that is very similar to rotations, but they are actually called hyperbolic rotations. So the first definition, in order to make that precise, the first definition is the rapidity. So the rapidity associated to a speed u with absolute value of u smaller than c is given by phi of u equals tangent, arctangent hyperbolic of u over c. Okay? So if you have u between minus c and c, you define another variable, phi of u, which is given by this arctangent. Now, you may have drawn before, this arcotangent in Mathematica or something. You will see that if you draw this, this is phi of u, this is u over c, this has singularities as u approaches c and minus c, and the arcotangent behaves something like this. Okay? So that the rapidity and the velocity are in one-to-one correspondence in this region, in the region in which the absolute value of u is smaller than c. Okay? So we don't lose any information by talking about the rapidity. All right? So instead of the velocity, we will use the rapidity. Why not? Okay? What happens if we do that? Okay? So what happens if we do that is that we get a few very cool formulas. If you have this, for instance, you have that, for instance, gamma of u, defined here, in terms of the rapidity is cos of the rapidity phi. Very cool, right? And u over c, gamma of u, is sinh of phi. Okay? That's quite cool, looking good. Then, if you take these two things and put them into the Lorentz transformation, let's put it here. So gamma of u, 1, u over c, u over c1. What is this? Cos phi, sinh phi, sinh phi, cos phi. Does it ring a bell? Do you remember how a rotation looks like? Okay, a rotation looks very similar. It's cos, sine, minus sine, cos. This is like a rotation, but in a space where one dimension is different because it's the time. Okay? Yeah, we just did a change of coordinates. Rather than using u, the velocity, we use this rapidity. And if we use the rapidity, the Lorentz transformation is like this transformation. Okay? And something super cool that shows that the structure is a structure of a group is that if you do the product of matrices, cos phi 1, sinh phi 1, sinh phi 1, cos phi 1, sorry, so cos phi 2, sinh phi 2. Is it okay if I use this instead of writing cos? Thank you. Sinh phi 2, cos phi 2. And you do this matrix multiplication, and you use identities between coses and sinches. You get something beautiful. Cos of phi 1 plus phi 2. Sinh phi 1 plus phi 2. Sinh phi 1 plus phi 2, and cos phi 1 plus phi 2. Okay? So that in terms of the rapidities, this matrix multiplication is just addition of phi 1 plus phi 2. Okay? Very much like rotations. If you have a rotation by an angle pi over 6 and another angle pi over 6, this is the same as pi over 3. Right? Because you can basically add up the angles. All right? So this tells that these matrices form a group. And the inverse, I will write one more formula, is just obtained by reversing phi to minus phi. So if you just do the inverse of a Lorentz transformation, that's like inverting rapidities. And let me write for you addition of velocities in terms of rapidities, because it's very cool. Phi of omega, so it's the velocity, sorry, that we derived before. This one here, in terms of rapidities, phi of omega is phi of u plus phi of v. That's it. Okay? So, if you use rapidities instead of velocities, the rapidities just add up. Okay? So, what happens is that the rapidities go back to Galilean transformations, right? For very small velocities, and that's why you get Galilean transformations. And you can show that this is equivalent to this rule that we found before. Okay? Now, you may have heard about integrability. I am not sure whether you have heard that concept. So basically, in every single problem, or in a lot of serious problems in research having to do with relativity, you will be using rapidities. You will not using the velocity of particles. Okay? So this rapidity is a very important concept. And yeah, and it's a concept that makes manifest this group structure of the Lorentz transformations. So it's quite cool. So we are kind of back to addition, but with these rapidities. Thank you very much.